Masteria Education.
Benzene was first created, or when it was first discovered, there were different theories about what it would exactly look like. So this model here that I've just shown us, this is called the Delocalised model for benzene. However, there exists another model as well, which we need to know about, and that's called the Kekulé model. So what happens in the Kekulé model is it's slightly different in that it still has the same formula. So this benzene here has 6 carbons and 6 hydrogens. This model here also has 6 carbons and 6 hydrogens because of the double bonds. However, this model is clearly different in that instead of it being a delocalized ring, you've got several double bonds seen here, alternate double bonds essentially. And this is called the Kekulé model. Now, there are several reasons why the Kekulé model isn't preferred to the delocalized model. There's actually 3 reasons that we need to know about. Reason number 1 is to do with its reactivity. So in the Kekulé model, it has alkenes in the sense of it has the functional group of an alkene. This means the Kekulé model should react how an alkene should react. Now, we know from earlier in the course that alkenes can react very easily with bromine in order to form a molecule like this in an addition reaction. However, what we actually find is when we have benzene, it doesn't react with bromine. So that means this model is much less likely. So one reason is because it doesn't react with bromine. And that's reason number 1. Reason number 2 is to do with the bond lengths. So in chemistry, bonds have different lengths depending on the strength of those bonds. So single bonds versus double bonds have different lengths. When we have this model, the Kekulé model, we would expect that all the bonds would be different lengths. So you'd have single bonds and you'd have double bonds with differing lengths. However, what we find is all the bonds are actually of equal length. And this weighs a lot more into this delocalized model where all the bonds are actually the same, rather than Kekulé where you've got some singles and some doubles. So that's the second reason. So first was reactivity, second was bond lengths. The third one is to do with the enthalpy of something called the hydrogenation. This is basically the energy required to add hydrogens to something. So when I have my C double bond, if I add hydrogens to it, we would form a molecule like this. Now, the enthalpy of hydrogenation for an alkene, like ethene for example, is about minus 120 kilojoules per mole. The exact number isn't super important, but you just need to know that it's exothermic. What we'd expect for Kekulé's model, therefore, is it would be 3 times that, because there are 3 double bonds here. Each double bond is minus 120, so we'd expect it to be about minus 360 kilojoules per mole. What we actually find, though, is that benzene's enthalpy of hydrogenation is less exothermic than that. It's around the 250s. Again, like I said, the exact number is not too important. But essentially what we find is it's less exothermic than expected. And it's quite important to use that wording of less exothermic, because it's not right to say it's less than expected, because minus 250 is actually greater than minus 360. So we can't say in an exam question it's less, we have to say it's less exothermic, okay? So overall, the delocalized model is preferred over Kekulé for these 3 reasons: its reactivity, its bond lengths, and its enthalpy of hydrogenation.
Thanks for watching our short video. Our full video is on our channel. Don't forget to sign up to our A-level revision courses. The links to these are in the description. And don't forget to subscribe for weekly content.